well, this is just to say that, there's firstly really many different exoplanets out there. And then secondly, there's really lots of stars in our galaxy and lots of other galaxies, and each star has at least one exoplanet. So there's like a huge number of different exoplanets around all the stars and all the galaxies out there. So it's actually quite a lot of diversity. So here we are. I would like to end on this, again, idea of this grand collage. It's where we started. So, if you look at different places in the universe, you see that there are a lot of really very different objects. Luckily, so these cosmological models and galaxy growth models help us make sense of the things happening. So they kind of tell us like what is the place of each of these observations in this grand picture, so to say. So I hope that from today I have conveyed that there's quite a lot of diversity in the events which are happening in the galaxies, but overall, they have all some influence on each other. For example, this type 1a supernovae produce iron, which we observe here on the Earth, for example, or the black holes we can measure, of course, but also are sit inside the galaxies and somehow describe how the galaxies form, or somehow related to how the galaxies form. So I mean, there's quite a lot of connections between these different objects and phenomena which are over there. And just the fact that we see so many exoplanets, one can but wonder like how typical is the solar system, how common is our system among these other exoplanets, like why are we special, for example. So there's quite a lot of things going on in the universe at the same time. So that's my message.
Thank you, Alexey. That was a very informative session, and it was an honor having you today. If any of the participants have any questions for Alexey, please raise your hand in the Zoom meeting and speak one at a time.
Hello.
Hello.
Yeah, I have a question. How is this new James Webb Telescope going to help us in finding new exoplanets?
Thank you so much for your question. And it's a great question, by the way. So in case you have been following the news, great. If you have not been following the news, there was this new very important telescope launched just yesterday to space. It's called James Webb Space Telescope. So everybody has heard about Hubble. Hubble Space Telescope has been giving us lots of beautiful pictures of the galaxies and star-forming regions and planets. James Webb Space Telescope is going to be, or it is approximately 5 times more or larger in size than Hubble Space Telescope. It's going to be much more sensitive than Hubble Space Telescope, and it's also going to be looking at the objects in infrared as opposed to Hubble Space Telescope, which was looking in visible light. So it will definitely be able to tell us a lot about exoplanet formation, I believe, because exoplanets form around stars, and the planet formation happens when the stars are very young. And when the stars are very young, they typically are formed in dense molecular clouds. So maybe a little bit like we see on this picture here. So that these dense molecular clouds in the galaxy where the gas has condensed, and in this condensed gas, the stars can form because the gas is dense. And because the stars are forming, there are also planets forming around them. But since the stars are inside molecular clouds, it's kind of hard to see them. So to be able to see them, it's good to look in the infrared light because the dust doesn't scatter infrared light as much. So this James Webb Space Telescope is going to be able to look deeper into molecular clouds, but also it's going to be about 10 times more sensitive than Hubble Space Telescope. It's going to be able to give us much better pictures of how planets form around stars. So I think just at the very least, it will give us much better images of the planet formation in the early stages, and perhaps tell us what is happening in these protoplanetary disks. And it will certainly help us observe the atmospheres of exoplanets. So because it will be also much more sensitive, so it will tell us about the elements in the atmospheres of planets around other stars, which is something we cannot yet do in very big detail. So I mean, James Webb Space Telescope is going to be important not only for exoplanets but for many other fields. But so it's actually a very happy thing that it was launched successfully yesterday. Thank you again for your question.
I have another question. Since we are knowing that our universe is expanding as per Big Bang theory, so this also affect the planet also, like their size also increase. I mean, somehow they got solar dust, and because of expansion of universe, the size of planet also expand. I mean, it's maybe a hypothetical question, but
well, it's actually quite a reasonable and very good question. I think the current understanding is that also this expansion of the universe, people sometimes call it Hubble flow. Hubble flow is called that way because the universe, so the galaxies recede from each other or go away from each other following the Hubble law of expansion. So the further is the galaxy, the faster is the expansion. So the current understanding is that the galaxies and the solar system as well are detached from the Hubble flow because they are gravitating towards each other and somehow it counteracts the universe expansion. There are models which have been trying to incorporate the universe expansion into the solar system motion or the galaxy motion, and they show that the effect is really very negligible. So I think in the current understanding, so there's no measurable way of determining the universe expansion through observations of galaxy or our solar system. So that's on one side. But then we know also that the universe is going to be expanding onwards and onwards. So in fact, it's expanding faster and faster. It is an accelerated expansion. So it's accelerating. So it's expanding faster and faster. So if we wait for another age of the universe, like for another 10 billion years, or maybe like 100 billion years, the universe will be expanding so fast that at some point, I mean, after this some number of hundreds of billions of years, so many times the age of the universe, it will be expanding so fast that actually it will affect us a lot on even small scales. In some scenarios of like what will happen to the universe, there's this scenario called Big Rip. So at some point in the future, at infinite time, the universe will be expanding so ultra fast that even the atoms will be affected. But it's very speculative, so we don't know if this can happen.
Okay, so my question is, why are galaxies like disc shaped and not like any other shape or like spherical?
That's a very good question, and in fact, to be completely fair, there are quite different shapes of galaxies. I maybe could show the image from somewhere in the beginning, something like this. So in reality, yeah, okay. So the reason why the universe has many galaxies which are disc-shaped is because if you form a galaxy, then there is this thing called angular momentum conservation. So if you have two objects spiraling in, then they have to conserve this sort of rotational momentum. And it means that if you have two objects which kind of merge together and form sort of like a clump, then they still want to rotate, and this angular momentum conservation makes them kind of look kind of like disky. And on top of that, when they look disky, they also tend to radiate a lot of energy. So the energy radiated makes the disks kind of colder and they kind of become thinner, but angular momentum cannot be radiated. So the merged, small sub-galaxies stay as disky galaxies. That being said, also sometimes galaxies merge in such ways that so they spin, but also they merge in opposite direction to the spin, so that they actually turn into so-called elliptical galaxies. So here on the image, I guess probably some of the galaxies, well, I mean, they are irregular in shape. For example, here, they're just merging right now, or some of the galaxies like these perhaps are, roughly speaking, disky. And also early in the universe, also some galaxies, they were formed very massive because initially the gas is inflowing. So there are a lot of sort of small building blocks also left from that epoch, which is called dwarf galaxies. They also look much more irregular than disky. So I think short answer is that many galaxies look disky because of angular momentum conservation, which requires that the galaxies remember their sense of rotation, but also many galaxies are, well, a fraction of galaxies, approximately 30% of, so they're not disky, but they're either elliptical, or which means that they're kind of like blobby, like look like ellipsoids, or they might be even much more regular in shape. So, for example, dwarf galaxies.
Got it. Thanks.
Okay.
So I had a question regarding black holes. So in generally, we say black hole is an object which has mass, and we associate properties like Hawking radiation also is tend with it says that it loses energy and it's eventually loses its mass because mass and energy are related. So at the same time, we also say that black hole uh, tends to be a hole because it does not allow the space-time to be continuous. So we use both the terms for it. So how is it possible? Like we can't say a thing which is a whole and it also has a mass. So how do you use both these terms at the same time for the single thing?
Yeah, I see your point. So basically, yeah, so we say that black holes are black holes, and indeed, so if you try to describe black holes in general theory of relativity, they actually are like singularities, or how to say, they are discontinuities in the space-time. So they're like holes, but at the same time they kind of have mass. So and the way we see them really is perhaps, let's see. So if you have a black hole, then the thing is that, okay, so here's a black hole. Imagine, for example, somebody out here is trying to study the black hole. So, for example, there's a spaceship flying around the black hole here or there and tries to see what are its properties. So, and the point is that if we are outside of the black hole, then especially if we are sufficiently far away from the black hole, for example, more than 10 or 100 times its radius, then it will really appear as if it's just a mass of, like, massive object of that mass. So, for example, when we looked at supermassive black hole in the center of our galaxy, it's observationally, it just looks like there's some very centrally concentrated mass which makes stars move around it. So, like, it behaves from far away, or people in relativity say at asymptotic infinity, it behaves like a Newtonian mass. So it behaves like a ordinary gravitational object, and this way we can associate a mass with a black hole. But the reason why we like this overall thing about it being a hole or singularity and it being a physical object, I think the overall picture is that, well, okay, so general relativity says that a black hole is inside looks like this. So black hole inside looks like a really empty area, because I mean, even light cannot escape. How can a matter stay kind of static in this region? So it all has to fall to the center. And according to relativity, indeed, there is a singularity, so it's like infinite concentration of mass, because everything has to fall to the center. So there's very, 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 very much mass, like few solar masses, well, we would expect to be in very, very small place, which is comparable to this sort of like one single point of relativity. But then we also know that general relativity breaks down. So, I mean, for example, if we expect any quantum effects to take over, so for example, we know that one cannot have infinitely precise locations of particles in quantum mechanics. So if you take any particle like electron or proton and try to make it infinitely accurately located or perfectly located, then you would have to spend infinite amount of energy, in fact, to locate a particle within like really up to one precise point. So like it's an idealization. So in other words, if you want to say that one solar mass is located in one single point, it would be also unphysical, because one would have to actually spend energy. So it's like it's contradicting quantum mechanics. So put very shortly, we believe that in the centers of black holes, there's this quantum gravity, in fact, regime, which actually makes the central singularity not really holes, but some kind of quantum gravitational blobs, which we cannot really see, but there's some kind of interplay of quantum mechanics and gravity there. So that's kind of like strange state of matter. But so inside a black hole, it's not really a hole, it's some kind of quantum gravity thing, but far away from black hole, it looks like it's just point mass of some physical mass. Hope that somehow clarifies it. Although,
so,
I mean,
can you
we
help
don't
me
have
out with any source of information where I can read about the thing which you told that it contains that quantum something, so I can read about those things?
I can say that, okay, so general relativity in itself, I mean, there's quite a lot of good courses and books there. I'm sure you can find some. I mean, I personally liked the books by Stephanie Wald and Misner Thorne Wheeler. So I mean, they were quite classical. But I mean, like there are quite many really good texts on relativity, and I'm sure you can find good ones by many authors. For this quantum gravity things, so there's no theory of quantum gravity yet constructed. So there's no unified theory which everybody accepts how these quantum and gravitational things should interact, but everybody acknowledges that there should be something quantum gravitational, because quantum mechanics seems to contradict general relativity in these extreme regimes when you try to make objects point-like or something like that. So I mean, I would mostly recommend trying to look up references to different theories of quantum gravity, but not dig deeper, but just to get general understanding. And definitely would recommend checking out, well, on top level, string theory, loop quantum gravity, causal dynamical triangulations. So they are all different approaches to unifying quantum and gravity. So a string theory is classical one, kind of most established, but it's not tested yet. And loop quantum gravity has been developed in quite much detail, and they have models of black holes within their theory, I believe. Causal dynamical triangulations is yet another way to try to construct a theory which is both quantum and gravitational, but it's a grand problem of physics yet to find a theory which is both describing gravity and includes quantum effects.
And I want to add another question. Like when you talked about that, the things also go at the quantum level. So when we describe a thing which is relatively big, we use the relativity theory and all. And at this, because the nature of the forces when we go at the quantum level is different from the nature of the forces when we go at the larger levels. So how can we describe a thing which is working on a in a larger level by using the forces of the smaller level, like quantum forces, like the strong nuclear force, and the further we go down the forces between quarks and all. So how can we use those to describe a thing which is for relativity?
I think the way I see it, at least, is that the quantum gravity effects are important for the things happening in the very center of black hole, and they are important maybe on the surface of black hole where there might be the processes leading to Hawking radiation. So I mean, if you want to study these locations in detail, then one indeed cannot describe it, or cannot really, I mean, model that in much detail by using just relativity alone. But if you are looking at an object from far away, then its quantum nature is not really relevant for the gravitational forces it produces far away. So in that sense, we can understand it from relativity point of view. So put it another way, I mean, most of the processes related to black hole mergers, for example, or to black holes themselves, are pretty well understood until we really have to understand what happens close to the very, very centers of black holes. So I would say perhaps that's the reason why quantum effects do not affect much the gravity. But I mean, like, you know, I mean, we cannot say that we understand everything without having a full theory. So, like, in principle, there might be some interesting things happening, but just, yep. But the expectation is that we are working on scales, or we are interested usually in scales which are much larger than the scales in which quantum mechanics matters. So we could kind of have an effective classical theory for that.
Okay, I got your point. Okay, thanks for the answer.
So I think we do not have any more questions, and we've also run out of time. So I think that will be the end of today's session. Thank you everyone for joining, especially Alexey for making time out of your schedule.
Thank you so much. It's been a great pleasure.
Thank you.
Thank you.